Hello everyone, thanks for watching this video. Today I'm going to share our work, ADDNet, Attention Unit with Dilated skip connection and a dense connected decoder for retinal vessel segmentation. The work is done by Dongqing Huang, me, and Yue Zhang. Background and motivation. Retinal vessel segmentation in front images plays an important role in computer-aided diagnosis. As the only blood vessels that can be obtained without trauma, retinal blood vessels are of great significance for the detection of diseases such as diabetes, hypertension, and retinopathy. However, manual segmentation of blood vessels is a time-consuming task and needs to be performed by a professionally trained and experienced physician. Therefore, it is necessary to accurately segment blood vessels in front images in order to make an efficient diagnosis of the disease. Our motivation is inspired by the excellent performance of UNIT, the extent of attention mechanism, and the feature fusion, and the problem of semantic gap. UNIT is undoubtedly the milestone of biomedical image segmentation tasks. Its symmetric encoder-decoder structure has been widely used in medical image analysis. The attention mechanism in deep learning is inspired by human attention and is widely used in various types of deep learning tasks, such as natural language processing, image classification, and speech recognition. Semantic gaps are usually caused by concatenating the features directly, and the feature fusion is also an important way to improve segmentation results by fusing feature maps of different sizes. Our model is based on encoder-decoder structure. The network consists of 4 encoder blocks and 4 decoder blocks. Every block is followed by a attention module. The corresponding blocks are bridged by dilated skip connection to reduce the semantic gap, and the decoder blocks are densely connected for feature fusion. To avoid overfitting, we utilize drop block as a regularization method, different from dropout randomly dropping independent units. Drop block discards the contiguous region of a feature map together. The new Conv Unit is constructed by convolutional layer followed by drop block, a batch normalization layer, and a value activation. Attention module. Human attention mechanism is derived from intuition. It is a means by which humans use limited attention resources to quickly screen out high-level information from a large amount of information. In our work, the attention module includes both channel attention and spatial attention. Channel attention was proposed to reweight filter responses in 2 steps: squeeze and excitation. Squeeze is achieved by global average pooling to embed global information, while excitation is aiming to capture channel-wise dependencies. In order to fully capture local cross-channel interaction and make correspondence between channel and its weight, we make all channels share the same learnable parameters. Follow the same design paradigm, we propose the spatial attention. The feature map is compressed through channel dimension instead of spatial dimension, and a 2D configuration is adopted to learn corresponding spatial information. One of the reasons Unit achieves the current segmentation result is a skip connection structure. However, the features coming from the encoder block are supposed to be low-level features, as they are computed in the earlier layers of the network, while the decoder features computed at deeper layers are supposed to be higher-level features. Concatenating the features directly ignores the problem of semantic gap. To solve this problem, we insert multiple dilated convolution layers along the skip connection. Those convolution layers can not only reduce the semantic gap between different stages, but also maintain the relationship between local and global context information. We reduce the number of convolution layers and the dilation rate of each convolution layer when the feature goes deeper. Dense connect decoder. Fusing features is an important means to improve segmentation performance. The low-level features usually contain more precision and detailed information, but less semantical, while higher-level features contain richer semantic information, but the spatial information is lost. In the process of fusion, it is inevitable to upsample smaller feature maps. In our work, Pixel Shuffle is adopted to upscale the feature map, different from deconvolution or interpolation. Pixel Shuffle introduces no parameter. It only rearranges the pixel, which can not only upscale the feature map, but also reduce the thickness of the feature map. For example, when the tensor with 256 channels in the decoder is enlarged by 16 times, the number of channels is reduced to only one, which extremely decreases the computation cost. At the same time, the dense connection of decoder effectively solves the problem of gradient disappearance in the process of backpropagation. Experiment. We conduct experiments on 3 datasets: Drive, TraceDB1, and Style. Drive contains 40 images. The 33 images do not show the sign of diabetic retinopathy, and the 7 images show signs of early diabetic retinopathy. The Style dataset consists of 20 images. The TraceDB1 consists of 28 images collected from 14 children. During training, color images were converted to grayscale images, and then we exploited contrast, limited adaptive histogram equalization to improve contrast in images. After that, we applied the rotation, translation, flip, and noising to images for data augmentation. To make a qualitative evaluation of the experimental results, we use accuracy, sensitivity, specificity, F1 score as performance evaluation matrix. These are experimental results on Drive dataset. We achieve best result on sensitivity, accuracy, and AUC. The F1 score is slightly lower than DE unit, and specificity is lower than RV segment. The area under the ROC curve is 0.9856, and the area under the precise recall curve is 0.9077. And these are experimental results on stale dataset. We achieve best result on sensitivity, accuracy, F1 score, and AUC. The specificity is lower than the internet, and the area under the ROC curve, which is 0.9915, and the area under the precise recall curve is 0.9309. And these are experimental results on TraceDB1 dataset. We achieve best results on all 5 matrices. The area on the ROC curve is 0.9906, and the area on the precise recall curve reaches 0.9131. By analyzing these tables, we found our model tends to oversegment when it encounters more capillaries in the picture, which results in the lower specificity in drive and stale datasets, and indirectly lowers the FE value. Conclusion and future work. We propose an improved unit-based model. Attention modular is introduced to enhance the features. The meta gap is relieved by dilated skip connection. In Decoder, the pixel shovel is adopted for feature fusion. Compared with state-of-the-art methods, our method achieves good performance. In future, we will improve our network, especially those incoherent and ambiguous pictures in the segmentation. We will explore the feasibility to retain the model whenever new images have to be segmented. Our work will further be extended to the segmentation of 3D data and integrated into the reconstruction workflow. That's all. Thank you for listening.